Okay, it's time for the last section in Chapter 6. This section is about indeterminate forms, and we'll talk about what that means in a second. I just want to say that it may seem odd that this section is stuck here, and it is odd. This section is all about limits, so you might think we should have done it way back before we even learned about derivatives. We couldn't do that, as you'll see in a minute, but after we learned about derivatives, we could have talked about indeterminate forms and L'Hopital's rule, which is what we're going to talk about now. But really, all the good examples involve exponential and log functions, so we wouldn't have been able to do anything fun with it, so I think that's why the book waits and sticks it here. Anyway, this is about how to do certain types of limits a new way, and will let us do a lot more limits than we could do before. Okay, so indeterminate forms are limits that I think of as being pulled in two directions, and some of these we already know how to deal with. So here's an example of a limit pulled in two directions. If you have the limit as x approaches 2 of x squared minus 4 over x minus 2, if you think about the numerator, that numerator is going to 0, and 0 over anything we think of is 0, right? 0 over whatever is 0. However, the denominator is also going to 0, and anything with a 0 on the bottom should be undefined or maybe approach infinity. So the numerator is trying to pull this limit to 0, and the denominator is trying to pull this limit towards infinity. And so overall, the limit's being pulled both ways, and we don't know where it's going to land. Well, this particular limit we've been able to do since the beginning of last semester. This is called an indeterminate form of type 0 over 0 for somewhat obvious reasons, right? It's a fraction and both its numerator and denominator approach 0, each of them independently. So it's 0 over 0, and then you have to do something with it. With this particular one, we resolved the ambiguity by factoring the numerator and then canceling, right? So you can factor the numerator as x plus 2, x minus 2, cancel the x minus 2's, limit as x approaches 2 of x plus 2 equals 4, and so that's the limit. Right? It's not 0, it's not infinity, it's somewhere in between. 4. Okay, the problem is you can't always do that. So here's another limit. It's a fraction. X approaches 1, natural log of x over x minus 1. Well, that numerator is going to 0 because natural log of 1 is 0. The denominator is going to 0 because 1 minus 1 is 0. So you've again got a 0 over 0 type of indeterminate form. But now, there's nothing I can factor or cancel or anything. There's nothing algebraic I can do to simplify this, so I don't know how to take that limit using the techniques from last semester. Right? It's not always 0 over 0. Here's another situation. This is a limit as x approaches infinity, but it doesn't necessarily have to be, but a limit as x approaches infinity of x squared minus 1 over 3x squared plus x. The numerator and denominator are each going towards infinity, right? Infinity squared minus 1 is infinite. 3 times infinity squared plus infinity, that's infinite 2. And the numerator is infinity, and infinity over anything ought to be still really, really giant infinity. But the denominator is infinity, and anything over infinity ought to be 0. So again, we're being pulled towards infinity, and we're being pulled towards 0. So is it 0, or is it infinity, or is it something else? With this one, we multiplied the top and bottom by the highest power of x, which was, or 1 over the highest power of x, 1 over x squared. When you do this, you simplify, you get 1 minus 0 over 3 plus 0, you get a third. So it's not 0, it's not infinity, it's something else, a third. But again, you can't always do this. You can't always multiply by the highest power of x because sometimes it's not powers of x that are the problem. So you have an infinity over infinity situation. It's indeterminate. We don't know what the limit's going to be. So to deal with these, we have another theorem. This theorem is called L'Hopital's rule. I'm assuming L'Hopital was French. He might have been Swiss or something instead. I don't really know much about him. Sometimes his name is written without the S and with a little accent circonflexe above the O, which is a little pointy hat thing. That's not the way he wrote it. He wrote it this way, Le Hospital, right? So L'Hopital's rule, it says the following. Let's say you've got two functions, and they're differentiable functions, so they have derivatives. And one of them, which will be our bottom function, g of x, its derivative is not 0 for x values close to a particular value a. But right at x equals a, maybe its derivative is 0. That's all right. But all the other values around there, the derivative is not 0. All right. And we're looking at f of x over g of x, and we're trying to take the limit of that. So one function over the other, this quotient. If that happens to be a type 0 over 0 or type infinity over infinity limit, then this theorem will apply. So infinity over infinity, I should point out, one or both of those infinities could be positive infinity or negative infinity. It's okay. That's still type infinity over infinity. If you've got a 0 over 0 or infinity over infinity indeterminate form, and both the numerator and denominator of your fraction are differentiable, then you can replace your limit with this other limit. All right? It is a different function. You have the derivative of the top over the derivative of the bottom, and miraculously, it has the same limit as the one you were trying to figure out. Okay? I want to make 2 points here. The first point is that we've changed the limit. We've replaced the numerator with its derivative, and we've replaced the denominator with its derivative. So this can completely change what the function looks like. But the limit will be the same. That's what L'Hopital's rule says. The second point I want to make is what we are not doing is taking the derivative of that whole thing in the limit. We're not taking the derivative of f of x over g of x. If we were, we'd have to use the quotient rule to take the derivative of that quotient. This is different. So we're not taking the derivative of the function inside the limit. We're taking the derivative of each piece of the function independently. The derivative of the top and the derivative of the bottom. And this, you only do this when you're using L'Hopital's rule to take limits, not when you're taking derivatives for some other reason. Okay, so let's see this in action. The limit we were stuck on earlier that we didn't know how to do because we couldn't factor anything was the limit as x approaches 1 of the natural log of x over x minus 1. Now, what happens when x is approaching 1? Well, the natural log of 1 is 0, and 1 minus 1 is also 0. So we get a 0 on top and a 0 on bottom, type 0 over 0 indeterminate form. That means that this limit that we want to do, we can replace with the limit of the derivative of the top thing over the derivative of the bottom thing. That is L'Hopital's rule, so I'll put a little L apostrophe H to indicate that I'm using L'Hopital's rule at that step. So I just replace the numerator with its derivative, I replace the denominator with its derivative, and that's L'Hopital's rule. The derivative of natural log x is 1 over x, the derivative of x minus 1 is 1, so I've really just got the limit as x approaches 1 of 1 over x. That's easy, that's 1. So this limit works out to be 1, this indeterminate limit. Okay. Here's another example. The limit as x approaches 0 of 3 to the x minus 4 to the x over x. So first of all, we have to decide what's happening as x approaches 0. 3 to the 0 minus 4 to the 0. 3 to the 0 is 1, 4 to the 0 is 1. This is 1 minus 1, that's 0. On top, on bottom, it's also 0, so we have a 0 over 0 type limit. Therefore, we can use L'Hopital's rule. Okay. L'Hopital's rule says take the derivative of the top. Now, to do the derivative of the top, you have to remember what the derivative of 3 to the x is. It's the natural log of 3 times 3 to the x. And the derivative of 4 to the x is the natural log of 4 times 4 to the x. And then you replace the denominator with its derivative. So the derivative of x, that's just 1. And now what happens when x approaches 0? Well, as x goes to 0, 3 to the x is 3 to the 0, which is 1. And 4 to the x is also 1. 4 to the 0 is 1. So we've got natural log of 3 times 1 minus the natural log of 4 times 1, and that's all divided by 1. And so it's natural log of 3 minus natural log of 4, but properties of logs say that's the same as natural log of 3/4, if you want to combine it into one thing. Okay, so this indeterminate form limit turns out to have a value natural log of 3/4. That's some negative number. Let's see one more example. X is approaching negative infinity, and I want the limit of e to the negative x over x cubed. So let's see, we have e to the negative infinity, that's e to the infinity, and e to really giant numbers is really giant numbers, so that's infinity. On the bottom I have negative infinity cubed, which is negative infinity, so this is an infinity over infinity type. Even though the bottom is negative, it's still an infinity over infinity type. So I get to use L'Hopital's rule. That is, I replace the numerator, e to the negative x, with its derivative. The derivative of e to the negative x is e to the negative x times the derivative of the stuff negative x, so that's negative e to the negative x. And I replace the denominator, x cubed, with its derivative, 3x squared. But now again, when I see what happens when x approaches negative infinity, the numerator is now negative e to the negative infinity. Negative e to the infinity, that's negative infinity. And the denominator is 3 times negative infinity squared, that's infinity. So again, I have an infinity over infinity type. That was a L'Hopital's rule, I forgot to write it. But since I still have an infinity over infinity situation, I get to use L'Hopital's rule again. That is, I get to take the derivative of the top, which now goes back to being e to the negative x, and the derivative of the bottom, which is 6x. But hey look, e to the negative x is approaching infinity, and 6x is approaching negative infinity, so I still have an infinity over infinity situation. So I get to use L'Hopital's rule again. The derivative of the numerator is negative e to the negative x, and the derivative of the denominator is 6. Aha, but now I don't have infinity over infinity. I have infinity, or rather negative infinity, over 6. And negative really giant numbers divided by 6 are still negative really giant numbers, so that's negative infinity. And so this limit equals negative infinity. Sometimes indeterminate form limits work out to 0, sometimes they work out to infinity, sometimes they work out to other numbers. It can be anything, that's why it's called indeterminate. Until you work it out, you don't know what it is. You have to determine the answer. Okay, so we've seen some 0 over 0 types and some infinity over infinity types, and you use L'Hopital's rule. Or sometimes there are easier techniques, the ones we would have done last semester. So use L'Hopital's rule or other techniques to do an infinity over infinity or 0 over 0 limit. There are other indeterminate forms besides those two types. 0 times infinity, right? Really tiny close to 0 things times really, really giant things. You don't know whether it's going to stay really tiny or get really giant or land somewhere in the middle. So it's indeterminate. Infinity minus infinity, sort of which infinity is bigger? Could be positive, could be negative, could be 0. Hard to tell. 0 to the 0 power, that's an interesting one, because 0 to anything ought to be 0, but anything to the 0 power ought to be 1. So is it 0 or 1 or something else? That's why it's indeterminate. Infinity to the 0 is also indeterminate, right? Because infinity to any power should probably be really big, but anything to the 0 power should be 1, so you got to see what's going on there. And 1 to the infinity is also indeterminate because really it's just close to 1 to really giant, and close to 1 to a high power should still be close to 1, but maybe the power is high enough that it gets big, and it's hard to tell. So these are indeterminate forms, and the way we deal with them, which we'll see in class, is you mess with it until you can get it to look like a 0 over 0 or infinity over infinity type of indeterminate form limit, and then you use L'Hopital's rule. So L'Hopital's rule is really the key. All these other indeterminate forms you just have to work with for a while before you can use L'Hopital's rule on it, because L'Hopital's rule only applies when you have a 0 over 0 or infinity over infinity form. Right. We will see lots of examples and get lots of practice in class, and I will see you there.